Close up your Chromebooks and let's go through one of these. All right, so we got a person traveling down the hill. We essentially did a problem very much like this before, right? The difference was you weren't dealing with coefficients of friction, and the kinematics part was this a little trickier than the last one we did. So our picture is pretty straightforward. If this is, maybe we can skip the picture and just go right to the free body diagram. So if this is the body, what are the forces acting on the body?
Gravity.
Okay, gravity. Okay, so we got gravity. In what direction is gravity acting?
Down.
Straight down. Okay, so what do I label that? mg. Okay. What else?
Normal force.
Normal force. Okay. Let's go ahead and I'm just going to trace in. Let's just say that this is going to be. There's the slope. We'll call that theta, just so it's kind of easier to orient ourselves. And we got normal force. In what direction is that acting?
Straight. Parallel to the slope.
Okay, normal to the slope, meaning perpendicular to the slope.
Yeah.
So there's our normal force. Okay, what else? Friction. That's it, right? In which direction is friction going to act? Up the hill, because he's sliding down the hill, right? So friction is going to be acting in that direction. So there's my kinetic frictional force. So those are the only three forces acting. Right? Now what do I want to do to that free body diagram?
Split up the orthogonalize it.
Orthogonalize it. Good. We want to make sure all the forces are broken up into components that are either going to be, and let's go ahead and assign what our directions are going to be. We're saying that that's going to be the positive, I'm going to call that down the hill positive for convenience sake. That's going to be the positive parallel direction, and that's going to be the positive perpendicular direction, right? So then the only one I've got to change is this guy down here. I've got to break up this mg into perpendicular and a parallel component. And if that's theta, then so is that. Right? Okay, so then let's redraw that one time. And the only thing we've got to change here is I'm going to substitute these two components for that one non-orthogonal force. Right, that one vector that's not lined up with the component directions. So what's this component going to be right here then? The one that's perpendicular to the slope. That's going to be what? mg cosines. It's going to be adjacent to the angle, right? Agree with that? Okay. So here's mg cosine of theta, which is 30.4. I'm just going to call it theta, so I have to write big numbers. And then in this direction, that's going to be mg sine theta. Everybody agree? I've just taken this guy and I've slid this one up to here, like so. Not drawn to scale, obviously, but that's all right, doesn't matter. Okay, so then there's that's what we need. That's our orthogonalized free body diagram. And that's what allows us to write the equations of motion. Okay, so what's one equation of motion given? You pick a component. Which one do you want to do, parallel or perpendicular first? Parallel. Okay, so the parallel component of the net force would be what? What's gonna be, give me one part of that, Ahmad, tell me, give me one parallel force that's acting.
I don't understand. Like,
So I wanna know, we've got this thing orthogonalized. Here's, you guys told me before, or we agreed that that's gonna be the positive parallel direction, and that's the positive perpendicular direction. So we wanna write the parallel component of the net force. Net force is just the sum of all the forces, right? So here, we're just gonna add up the parallel components. So what's a parallel component?
it would be
mg sine theta, yeah, and that's acting in the positive direction, right? So we get mg sine theta is positive. What's going to be a negative one?
Negative.
Okay, kinetic frictional force, right? That's the one that's acting in the negative parallel direction, parallel to the slope. Here's our slope. These two are the forces that point along the direction of the slope. One in the positive direction, one in the negative direction. So minus F sub k equals what? Parallel?
It's whatever.
Whatever it is, right? So we don't know what the acceleration is, but presumably that's maybe what we're trying to find, right? Because think what we're trying to get here. We know that the skier's gonna slide down, accelerate down this hill. After the skier skis 48.8 meters, the skier comes to some different snow, some wet snow, where it's stickier snow, right? When she hits the wet snow, then all of a sudden the kinetic friction increases, making the net force on the skier zero. So now she's just coasting along, not picking up speed in the wet snow, right? So we want to know how fast is she moving when she enters the wet snow, and then what's the coefficient of friction going to be, right? So we would need to know, in order to find out how fast she's moving, that just sounds like kinematics, doesn't it? Right, if we knew what the acceleration was and we knew what the displacement was, we ought to be able to calculate, we know what, does that make sense? We ought to be able to figure out what the acceleration is. Initial velocity is 0, right? Okay. So if we just knew what the acceleration was, we could probably answer that question, okay? But we don't know what it is yet, but net force equals, what's Newton's second law? What's net force equal to? Yeah, ma, right? So it's going to be m times the parallel component of acceleration, but that's all the acceleration, isn't it? Everybody agree? I mean, skier's only moving on the slope. So we'll just call it a, because it is the entire acceleration. So there's one equation of motion. Now what about the perpendicular components of the net force? What's a positive one? Normal force. Negative.
Mg cosine.
Okay, so minus mg cosine theta equals 0, because there is no perpendicular acceleration, right? And so there's our second equation of motion. Why is that one useful? What's it really telling us? They cancel each other out, true. So if I were to solve for the normal force in this case, yeah, good. Normal force, I would just add this to the other side. So the normal force is mg cosine theta, okay? So then what about this first one? We're trying to solve for A, aren't we? Okay. What's our model for a kinetic frictional force? What's our model for a frictional force? Frictional force equals, say it again? Okay, good, it's good. Coefficient of friction, so mu sub k, the kinetic coefficient, friction times normal force. And this is one that you can, conceptually this makes sense, right? Because the coefficient is a property of the materials, how slippery they are, right? The normal force is how hard are they being shoved together. So how strongly are they interacting, right? Okay, so we could make that substitution. That's just a definition, right? That's just what we know our frictional force always is gonna look like. So that could get plugged in up here in equation number 1. And what does that make equation number 1 then? So we end up with equation 1, call it prime. We just made one little change to it. We end up with mg sine theta minus this. Yeah, and we could plug in, we know what it is, you're right. We know what I just don't have to write it every time, so I'm just gonna call it theta. But it's 30 point, whatever it was, it's up on the board. So minus mu times normal force. And what is normal force? mg cosine theta, right? So mu times mg cosine theta equals ma. Okay, so ponder that for a second. Is there anything we can do to simplify that one?
Cancel the
We
m's.
can cancel the m's. What's that telling us? What are the physics gods telling us if the m's all drop out? What?
They're not necessary.
Not necessary. They're irrelevant. They don't have any impact on the answer. Okay? So this is insensitive to mass or independent of mass, our result. Divide both sides by m, and now we've got A. And we've got A in terms of all stuff that we know, right? We know what theta is. That's 30.4. We know the coefficient of kinetic friction is 0.198. And we know G, and that's all we need, right? So we end up with A equals, I could factor a G out front, couldn't I? Don't have to, but I could. And then I'm left with just sine theta minus mu cosine theta. And let's just plug in values. So what's that give us? You guys remember those values, I bet. 30, was it 30.8? Is that right? 30.4. Okay, so we get 9.8 times the quantity. Sine 30.4 minus, what's mu, 0.198. Cosine.
And mu is the coefficient of friction.
Yeah. Cosine 30.4. Close the cosine, close the quantity, and we get about roughly 3.3. Okay, we'll leave that in the calculator, right? Say it again. Good question. Okay, why isn't gravity negative? Because, well, you guys tell me, how come?
Because cosine.
Because it's
Because in this case, it's
our positive direction is
Yeah.
down-ish.
Yeah.
That's how gravity.
Does that make sense?
So,
Okay, so right, so G is actually equal to 9.8, and like we would say, for example, that if I drop a pen, in that reference frame, we would say that, that's the positive, we just have x, y, it's just falling vertically, right? So if the positive y direction is up, which is our convention, then we would say, okay, if that's what we're saying is up, then when I drop something and it accelerates, the acceleration would be, the magnitude is G, but it's negative because it's going down, right? We could, if we wanted to. We could just, go against the grain and say, well, let's make down positive, and that's fine. It would work in the problem, but we'd have to just be consistent throughout the whole problem then. Okay, in our case, we define down the ramp as the positive direction, and so, our acceleration is positive. Okay. Let's see, where were we? So we got about 3.3. Okay, and now this just becomes kind of a kinematics problem, doesn't it? Okay, we know what the acceleration is, and so if we go back up here, let me just copy this to the next page. Okay, so we'll start making our list of stuff that we know. So we know A is about 3.3 standard units. What else do we know? Because we want to know how fast is the skier moving at the end of the acceleration in the dry snow, right?
Displacement is 48.8.
Okay, so delta, we'll call it just S for position this time. It's not really X or Y, is it? So delta S is positive 48.8, right? Because we're saying positive is down the hill. What else? We know theta, but we don't really need that anymore. Right now, we're just talking about one-dimensional kinematics. We already used our theta, we used that to find A, right? Yeah, what about this?
Initial velocity.
Okay, good. So V naught is 0, and what are we trying to find? Final velocity for part 1, right? And how many parts are there to this problem? 2. Good, and there's definitely 2 chapters in our story. How do we know for certain there's 2 chapters? What changes that absolutely makes it necessary to have another chapter? What is it?
Change in
Acceleration. Anytime the acceleration changes, we've got to have, the final conditions from the first part then become the initial conditions of the new chapter, right? Because the acceleration changed. Okay, so for part 1, we're looking for final velocity. So what's going to be the equation that relates those? Fourth one, yeah, no time, right? So that's what, v squared minus v naught squared equals 2a delta s. And so v naught is 0, so that goes away. So then v is just going to be the square root of 2a delta s. So what's that give us? So square root of 2 times that, there's our acceleration, times 48.8. $17.9-ish, right? So V is about 17 point, we got 3 sig figs, I think, is that right? So about 17.9 meters per second for part 1. Okay, we got it in the calculator. Okay, questions so far? Right? And the steps, I mean, are you getting to the point where you can kind of in your mind, you can break this up into some logical steps, right? Think what we did, just to rehearse what we did. We drew a free body diagram, included all the forces up here, right, that were at work on our body. We orthogonalized that, we chose what our parallel and perpendicular directions and made sure all of the forces were broken up into parallel and perpendicular components. We could write the equations of motion, right, because we've got the sum of our parallel components. It's going to give us ma. And then there's no perpendicular acceleration, so the sum of our perpendicular components equals 0. That allowed us, it gave us an algebraic system that we could solve and calculate the acceleration, right? So we got the acceleration, then just did some kinematics. Once we know the acceleration, we just do one-dimensional kinematics problem, and that gives us our final velocity, okay? What about part 2? Now in part 2, what's changed?
acceleration.
Okay, the acceleration has changed. Now in part 2, what's really important about part 2?
Frictional coefficient changes.
Yeah, and in particular, what's going on here? There's a really important part of this
Net force is 0.
Net force is 0. Yeah, making the net force on the skier 0. So really, we can go back to this first page that we were on, and this is the same free body diagram that we're going to have for part 2, isn't it? Right? It's not drawn to scale anyway. So let's just, I'm not going to reinvent the wheel here. Let's just grab this one. And there it is, right? So for part 2, we get the very same equations of motion, but what's the difference? If the net force is 0, what's the acceleration?
It's equal to the frictional, kinetic friction.
Right, so everything we did over here is, we can essentially reuse all this stuff, right? The only difference is, what's that going to be instead? Because when she hits the wet snow, her net force is 0. So what's going to be the parallel?
0.
0. Yeah, so all this stuff is going to be exactly the same. In fact, we can just borrow everything. Let's do that. I don't want to do this over again. Okay, so there's all our work for part 2. All we're going to do is we're just going to make a couple changes. This is going to become 0, right? And so then when we come down here, we make our substitutions. Here's the equation we get. We know theta, we know g, we know everything except what's the one thing we're trying to find in part 2? Coefficient of friction. So there it is. We can just go down to this equation right here. We don't really need, this one's obsolete. And we're just going to solve this for mu, right? So if I solve that for mu, I'm already at the bottom. Gosh, I'm running out of pages here. I'm running out of virtual pages. So, oops. Okay, so we've got the equation then, that's equal to 0, right? So if I'm just going to add this to the other side, I can divide by g this time too, can't I? Right? And I just end up with mu cosine theta on the other side is equal to sine theta. So what's mu? Tangent theta. So tangent 30.4 degrees, right? What is that? Well, it's going to be about what? What's that going to be? 1/8. The 1 over square root of 3, but not quite 1/8. Well, 1/2 over, what is that going to be? Sine, that 1/2 divided by square root of here too. It's about square root, so it's about square root of 3, or 1 over square root of 3, right? Yeah, 1 over square root of 3. So that's going to be about
0.57.
0.57. Okay. So about 0.57-ish, right? What is it to 3 places?
0.577.
577, okay. Oops. Okay, so there's our coefficient. Okay, make sense? Okay, that's kind of, isn't that strange that the coefficient is just equal, in this case, just equal to tangent theta? It makes sense if you think about it, though. Only thinking about it? Right, because it comes from, I mean, really all this is just going to be, this is the perpendicular component, right, of gravitational force divided by mu times the parallel component, right? So it's the ratio of the perpendicular, or the parallel divided by the perpendicular, right? Doesn't that make sense? As this slope gets steeper, what's that gonna do? As the slope gets steeper, the parallel component's going to get larger, right? And the perpendicular component's gonna get smaller. Everybody see that? So what's that gonna do to the coefficient then? Well, the coefficient's gonna, does that make sense? Coefficient is gonna depend on, I mean, it's, this thing is gonna slip more easily, isn't it, as it gets steeper, right? Now, that's a little bit of a hokey way to think about it though, because the coefficient's a property of the materials, right? So we can't actually change the slope in this case. We did our measurements for a certain angle. But if those measurements were the same and the angle changed, then that would have an impact on what that coefficient had to be to make it happen, right? That's, I mean, you don't have to, that's not necessary to think about it that way, but I always think it's kind of interesting to try to interpret the results. Okay, questions? Okay, try it. Try these. These are hard questions. They really are. These are a lot going on there.